Okay, today we're gonna prove Lebesgue Dominated convergence theorem, very big theorem. So Lebesgue Dominated convergence. This theorem actually tells us that we can switch the limits in integration. Okay, so Lebesgue Dominated convergence. What it says first? It says that if Fn is a sequence of measurable functions such that if a measurable function on definitely measure space where S is a sigma algebra such that Fn converges to F pointwise, and if there exists G belong to L1 mu, we are gonna see what is L1 mu. If there exists G belong to L1 mu such that Fn of x absolute value is less than G of x for all n belong to n, then it says that limit n approaches to infinity Fn d mu is actually limit n approaches to infinity Fn d mu. But since Fn converges, so this means that f d mu is actually limit n approaches to infinity Fn d mu. Or another way we can rephrase it, that limit n approaches to infinity Fn minus f d mu is actually 0. Okay, that's what it is. So we can rephrase this thing, that Fn d mu approaches to f d mu. So first we are gonna see actually what is L1. So L1 is actually a Banach space which contains all measurable functions. So G is measurable. Okay, such that one norm is finite, where one norm is nothing but is the integral of G d mu. Okay, so if this value is finite and G is measurable, then the function will belong to L1 mu. L1 is a Banach space. Okay, so now to prove Lebesgue Dominated convergence theorem, so first what we need to show that limit n approaches to infinity Fn minus f d mu is actually 0. That's what we need to show. And we need to use actually Fatou's lemma. So we will see, we're gonna recall Fatou's lemma. So first of all, we want to show this thing is actually 0. So how can we show that? If limit exists, this means that lim inf is equal to lim sup. So that is kind of idea. So first of all, we want to recall Fatou's lemma. Okay, because that's what we are gonna use to prove this result. So Fatou's lemma says that if Fn is a sequence of non-negative measurable functions, then limit n approaches to infinity infimum, which is lim inf Fn d mu, is less than or equal to limit infimum n approaches to infinity Fn d mu. So now what we have in the assumption, so in assumption we have, so assumptions. So first assumption we have that Fn converges to f, and second assumption we have that Fn of x is lesser than G of x for all n belong to n, and our goal is this thing. Okay, so how we can accomplish our goal? It's easy to see that. First of all, what we have, so for each x belong to x, what we have fn of x minus f of x. By triangular inequality, this is fn of x plus f of x, right? Now since we know that, since in assumption we saw that, so since fn of x is less than or equal to g of x, okay, for all n belong to n, okay, and so what do you think? And fn converges to f, so what do we think? So surely then f of x will also be less than or equal to g of x. So this means that what we have from here, that this left hand side is less than or equal to 2 g of x, right? So that is the first thing. Now we can rephrase it. It says that actually 2 g of x minus fn of x minus f of x is greater than or equal to 0. Forget about x just for simplicity, so we just, okay, so this means that this is greater than 0. Now what do we think about this term? What Fatou's lemma says? Fatou's lemma says that you have a sequence of non-negative measurable functions. Now fn is measurable, that was an assumption, and it converges to f. So f was measurable, fn is measurable, the difference of two measurable function is measurable, g is also measurable because g belongs to L1, so g must be measurable. So the difference of two measurable function is measurable, and also it is non-negative. So we have also this sequence is non-negative measurable functions, okay. Now we can just go ahead and use Fatou's lemma. So what Fatou's lemma says now, so Fatou's lemma says that you have limit n approaches to infinity infimum of 2g minus fn minus f d mu is less than or equal to limit n approaches to infinity infimum and 2g minus fn minus f d mu. So if you can again recall in lim soup that in general limit n approaches to infinity infimum of an minus bn is not equal to limit n approaches to infinity infimum an minus limit n approaches to infinity infimum of bn. But if suppose an approaches to a, then it is equal to a plus limit n approaches to infinity infimum bn, okay, plus minus, okay. So now since fn converges to f, so we can use this property, okay. So then we can apply limit. So if we apply the limit and also if we split the integral, so this will be 2g d mu minus, and what do you think about limit n approaches to infinity infimum fn minus f d mu? So this is less than or equal to, so I wanna again split it, limit n approaches to infinity infimum of 2g d mu minus limit n approaches to infinity infimum of fn minus f d mu, okay. Proof is very easy, we are almost there. Now what do you think about this term? What do you think about this term? Since fn approaches to f, so fn minus f is 0, so this term will be 0, okay. So on the left side what we have 2g d mu is less than or equal to, since we don't have any, so it is again integral of 2g d mu minus limit n approaches to infinity infimum of what we have fn minus f d mu. So this is nothing but okay, one more time. So we have 2g d mu is less than or equal to 2g d mu plus limit n approaches to infinity infimum of minus fn minus f d mu. Now we know that lim inf of minus an is equal to minus lim sup, and also what about this term and this term? So definitely it is 0, so 0 is less than, this will be lim n approaches to infinity sup of fn minus f d mu, or minus lim sup, because so lim inf of minus an is minus lim sup. Okay, so and at the end what we got, actually this is nothing but what we got limit sup and approaches to infinity fn minus f d mu is non-negative, is less than or equal to 0. So if lim sup is less than 0, so this means that lim n approaches to infinity lim in is greater than or equal to 0. But since lim inf is always less than or equal to lim sup, so from then these two equations we got lim n approaches to infinity infimum of fn minus f d mu is equal to 0 is equal to lim sup fn minus f d mu. Okay, and if lim sup is equal to lim inf, this means that limit exists. And what is the limit? So limit n approaches to infinity fn minus f d mu is actually 0, and that was our goal. Thus f d mu is actually limit n approaches to infinity fn d mu. Okay, so now the application. So as an example, you can try, I'm gonna just write down the example. You can try evaluate 1 minus x to the power n cos n divided by x divided by square root of x 0 to 1 limit n approaches to infinity. So you are gonna see you are gonna use actual Lebesgue dominated convergence theorem. You need to actually, so this is your whole f of n of x, and you need to come up with g of x such that g of x belong to L1, and also this whole f of n of x absolute value is less than g of x, and then you can just switch the limit. You can this limit can come here, and then you can evaluate the limit and eventually integrate. Okay.